share my file, and then you can access my slide. So everybody can see my slide. Everybody, everybody can see my slide.
கீழே வியூவா இருக்கான்.
Hello. Okay.
Like that is it.
Okay.
Good morning, sir.
Morning. You can see my slide. You can access my slide. You can see.
No, sir.
No. Okay. I try to repeat again to share my file. Okay. Now everybody can see.
Yes, sir.
All
Yes.
right. Okay. Assalamualaikum again. Assalamualaikum and good morning. Today we are already in week 3, yeah. During this semester. So in previous class, I already introduced about eco and liberalization, yeah. So what differentiate within them, and also how this is happen, and then how to differentiate, yeah, and then also uh, how to solve, yeah, the problem if this happen in the room designer. So how to counter the effect of the eco and revitalization, yeah. So now we try to continue in week 3 about other topics, yeah, other topic. This one relate to the, I think relate the theory of wave, yeah, in the applied physics, yeah. So I think this one you are already introduced in the applied physics. So this one is just remind us, yeah, how to implement in the uh, vibration, in HVAC application. So today I would like to introduce HVAC applied acoustic and vibration on the explain the basic principle acoustic wave, and the second one is identify the distribution of acoustic, and the last one distinguish method of reducing acoustic effect. So I hope uh, after finish the class you can get the something idea from this lecture class, yeah, from this topic. So actually I would like to introduce first the wave uh, properties during propagation in the air. So actually, I would like start with the YouTube, yeah. But maybe because around the class with online, so difficult to like to share this YouTube. So you can access by yourself here the YouTube this one. So this video actually introduce how actually the um, sound, yeah, propagate in the air by uh, using, yeah, the air as a media. So actually they are through the molecule. So molecule itself actually same like the solid material. They have a molecule inside, but this one is maybe considered is with the low density, and maybe the hardness is lower compared to the solid. But actually, the principle of the molecule itself is same regarding to transfer the vibration. Yeah. So the molecule itself have the elastic properties. Yeah. So every molecule will be transfer the vibration by electricity, and then they have the impact, by themselves, and then the momentum will be occur. So remember in the maybe in fluid mechanics, yeah, they will already introduce how the momentum occur in the fluid system. So by the F equal to m dot multiplied by differentiate velocity. So m dot itself is mass, yeah, uh, quantity that apply multiplied by mass dot equal to density multiplied by uh, q. Q is mean the quantity, so the number of the fluid itself. So once the impact to the solid, the elasticity of the molecule will be have the reflection. Yeah. So this one also occur in the wave propagation. Yeah. When they start to vibrate to the air and the molecule will be impact each other and they will be bring the other, yeah, by impact or momentum activity, yes, and then hit to each other to transfer, yeah, from the starting beginner to other molecule until to the uh, energy become weak, and then we consider the vibration already lost. Yeah. So that's how the video described. Yeah. So molecule itself have the distance. Yeah. And then when the elastic already occur, and then the distance will be uh, happen. Yeah. Within the molecule, then they have the distance, yeah, after the impact. That one we can implement to the graph. Yeah. Uh, by sound wave frequency. Yeah. Maybe like this. Yeah. They have the distance. Yeah. And the maximum happen the impact, and then within them this become to zero, and then back again, impact again, and then complete to one cycle. Then from this uh, nature uh, phenomena, we can derive the formula, and then we can uh, what we can determine the calculation of the frequency, period, anything from this phenomena. So we go first to the frequency phenomena after the wave happen in the air. So the frequency itself, which is the number of pressure variation cycles in the medium per unit. So mean that, so we can determine, the cycle in 1 second. So from the formula itself, frequency with the unit hertz, and then we can derive the formula cycle over to second. So every second we can measure how many cycle occur, in the system, in the propagation. So we can define the frequency. So let's say, this one is a 1 cycle. Yeah. If the mention this one is 1 second, mean only one cycle. We have the maximum and then minimum. That one is considered to 1 cycle. So if more than this, maybe the frequency will be increase. Yeah. So let's say the cycle is more than one. This one the 1 cycle, one peak and one is a bottom. Yeah? Okay. And then maybe have a much of total of the cycle. That one is a high frequency. So if we compare to the period, time, t, time, or simply the number of cycle per second, and is expressed in hertz. Okay, if we try to solve the period, mean over to frequency. So mean how many sorry, how much time needed to complete one cycle. So one peak and one lower peak, or bottom. So how many we can collect, this result? How many time needed to complete in one cycle. So that one is opposite to the frequency. So I hope you can understand the definition about the frequency and also period. Okay, we go to amplitude. Yeah, as we know, the amplitude is a peak. Yeah, from the zero. Yeah, starting from the zero, and then we can measure the peak of the uh, wave itself. Yeah, so mean that the length, yeah, of peak, yeah, from the neutral or zero original position. Yeah, so we can measure that one is a amplitude. That's how to we try to simplify the definition of the amplitude. Yeah. So if we refer to the text, yeah, amplitude is defined by pressure change, which can be described by the maximum pressure amplitude, or we can um, denote by a notation is PM, P with a small p, and then M with a capital M. So we can define Earth amplitude or the root mean square RMS amplitude PRMS. So another parameter we can also measure by root square RMS amplitude, yeah, PRMS. So PRMS itself is the number average, yeah, from the peak. So we can measure by the PRMS is 0.707 from the amplitude. Mean that if amplitude is here A, and then the B is we can calculate by a constant number, this one, yeah, 0.707, yeah. So mean lower than the amplitude. So this one we can call first uh, RMS, root mean square. Root mean square mean that the instantaneous sound pressure are squared average, and the square root of the average is taken, the quantity. Yeah. So after formula, yeah, we can get the result is 0.707. So the formula is come from the over to 1 per square 2 square root time the peak amplitude. This one is a formula, and then we can get this number. All right. Sorry. And then we go to the period. Period is opposite from the frequency. Uh, so if we refer to formula, mean that T equal to super F, yeah, which is the time taken for one cycle of wave to pass a fixed point. Mean that to complete one cycle, okay, let's say the one cycle is one peak and one peak or bottom, yeah, peak positive, yeah, upper side and then a downside. So this one is called one cycle. So how many need required to complete one uh, cycle? So we call that one is a period, right? So now we try to measure the wave length itself. Yeah? How do we call we measure the wavelength? So the wavelength, based on the definition of the sound, is the linear measurement of one complete cycle. So once complete cycle, we can measure the length. Yeah. So how many? How much the length? Yeah. To from the origin position until to one complete the one cycle. So we can call by lambda. Yeah. We can call by lambda. So the logo is lambda. So lambda we can calculate. Yeah. By CO, mean that CO is a speed sound in the air. So actually they can define, yeah, by 341 meter per second is mean speed sound in the air. So actually depend on the temperature because of the, as we know, yeah, the density of the air depend on the temperature. So maybe different temperature, different speed of sound. But we can simplify. We can simplify by 341 meter per second, or in the British unit. By feet, we can use 1,120 feet per second. This one is at sea level, mean that based on the pressure at sea level. So mean that if the pressure is different, mean if you measure in the peak of the mountain, will be got the result different from the sea level. This one is measurement in the sea level and also by temperature because temperature will be changed by the uh, pressure and temperature. So the effect of speed sound also influenced by this parameter. Okay, that one is a CO. And then how about the F? So F, as we know, is the frequency. So you can measure the frequency. Frequency is 1 second how many uh, cycle occur or happen in the system. We can measure. So the wavelength, we can use the length unit in meter, or maybe we can the small size. We can use the nanometer or maybe micrometer. Depend on the uh, frequency itself. Sometimes maybe is small. So you can use nano, and if the frequency higher, and then if your frequency low, maybe the cycle is uh, also high. So maybe you can use the high unit. Measurement. Oops, sorry. Okay, this one is a condition, actual condition. If we measure within the frequency and time, so sometimes we can measure very consistent. Within the peak and time, and then the constant. But sometimes influenced by other condition, and then will be found like the another thing. So the peak is not always the same. Maybe change. So maybe have the other frequency condition influence in the system, and then this one the frequency may be influenced by several condition. Sometimes is higher, sometimes is lower. This one is a random condition. Okay, this one condition of the actual IQ in the fluid air can be considered air, maybe can consider the liquid system. The molecule will be transferred by heat, impact, same like this. So as we know, as mentioned before, so the elasticity of the molecule will be transferred the wave. So you can see the single of particle particle will be hit each other and then transfer this energy to the other, and then you can see some will be look like the close each other, and then some will be look like the have more far distance, higher distance, compared to other. So look like frequency. So this one we can measure the peak itself in the is a higher impact energy. Okay, pure tone. Pure tone actually we can measure. Okay, if you familiar with the music, so maybe you are already introduced the tone of the music. If you go to the piano, you can start with a sorry a low of tone. Maybe from the C with the low of octave. So as we know, we have several octave. Maybe the higher singer can go to the seven octave like Mariah Carey. So they will start the piano with low frequency. So this low frequency, they have uh, uh, standard standard area of the frequency octave. So this one is a lower of octave. This frequency is maybe is in middle of the octave. Yeah. So like uh, do re mi fa sol la si do. Okay, this one maybe this ring is a first octave maybe. And then we go more the higher maybe Do, re, mi, fa, sol, la, si, do. This one is considered other octave. Okay, this one consider the pure tone. Yeah? How I try to simplify the definition of the pure tone. Yeah? So the compression are region of high pressure due to the particle being close together. So when we start to activate the wave, and then the particle will be work, and then how the particle starting to work, to make the wave. That one we call uh, the basic, of the uh, octave. Yeah, the basic of the octave. We try to make the particle work, to wave, and then when we try to study when the particles start to wave, yeah, and then we can measure this one is a very low of frequency, and then with that, yeah, we can increase the pure tone level, yeah. So again, yeah, the second bullet here inform that reflection are region of low pressure due to particle being spread further apart. So then the frequency will be activate the particle, and then as mentioned the previous slide, they mentioned that particle will be hit and then will be go the far to find other particle to make the what we call phenomena of the impact, and then will be this one is we call reflection, compression will be have a high compression here, uh, and then will be spread again, this one is we call the wavelength, within the reflection compression, you can see from the slide, so the formula from the previous slide, because lambda equal to cu, over to f, and then if we change here to find c, and then we can get the new formula c equal to lambda f. Right? And then we can calculate c. C itself is a speed of sound, and then we can define in the 20 degrees Celsius is equal to 343 meter per second. That's why we how we define the uh, speed of sound, in the air. Okay, if frequency we change, this one is a pure tone. Okay, maybe we can uh, classify, the level from 36, and then 125, and then 250. Okay, then from this we can calculate the wavelength. So as we know from the previous slide, formula wavelength, C lambda equal to CO over F frequency. So we can complete this table, to calculate the wavelength. Yeah, understood? I hope you can understood. From this formula, we can define the wavelength. Wavelength is formula is lambda equal to CO here, CO over to F, and then we can complete this table. Okay, I hope you can try in your home, in your place, to solve wavelength based on this information, from the left column, and then you can define the right column. Okay, I hope you understood. Any question?
No, sir.
All right. So I proceed to next slide. Okay, now we go to the other definition. Some parameters, to measure. Okay, if you go to some engineering field, you need to define the parameter what you need to inform, to other the what parameter we need to calculate to inform that this higher or lower. Okay, if you go to the race, maybe you can define parameter, yeah, like acceleration and speed, yeah, to define this performance of the vehicle. Yeah, another is power. So you need to define, yeah, the study, yeah, the what parameter to describe this condition. Also in the wavelength, yeah, sorry, in the vibration, what parameter to measure to define this lower, higher. So need to be characterized, yeah, this parameter. So that's how we try to learn to study several field, yeah, and then we can derive what parameter to determine. So now we go to the fast Fourier transform, to describe something, what condition is happen in the uh, uh, propagation, yeah, wave propagation. So now definition fast Fourier transform, FFT, we can call FFT, was found by French mathematician Jean-Baptiste Joseph Fourier to show any complex waveform into a single frequency sinusoidal waveform through a Fourier synthesis. So actually, we can describe the condition, yeah? The condition, the wave itself. So sometimes the pattern like this, sometimes pattern like this. So we, as engineering, yeah, so as engineer, so should be described by the number. Anything in the engineering, it should be measurement to describe the condition. So the number of this, the number is so anything is represented by the number. So how to consider the vehicle is high speed, yeah, also by the number of speed. And then also another condition like the power of engine, yeah? So by the number, so represent by number. Also in the wave propagation also represent by the number. So describe something, condition in the wave propagation. Electronic filter could be added so that it only allows sound within the particular range of the frequency to be measured. This is all done using computer software such as MATLAB, and then using MFT frequency domain can be created from the time domain. So we need to describe by time. So what happened? How to describe this condition? Yeah. Okay, this one. If you go to the time, mean that the time will be constant, yeah, occur in the frequency, and the frequency we will reflect to the condition, what happened, yeah, in the that time, yeah. Okay, we can plot, yeah, and then we can describe the condition, one pattern to one pattern condition. Okay, sometimes the condition, yeah, like the maybe in electrical they very familiar to describe something in the wave graph, like the voltage, yeah, to the time, and then also ampere to the time, yeah, so described by this like the wave propagation condition, yeah, same like the sound also, so they will describe by the graph by versus again to the time. So what happened in the during the time, and then it described by the graph, yeah. So that one we call the FFT, yeah. So in the frequency domain, we can get a single peak, and this is because we have a simple sine wave of high frequency graph to show sine wave of a lower frequency and how it become peak again in the frequency domain, but this time has a lower value. So this one is a value. So again, a value. Number is very important in the engineering. Graph 3 shows a more complex waveform where two sinusoidal waves of different frequency are added together or we solve, we say superimpose the frequency domain, then show that we have two frequency. So sometimes when we measure the frequency, sound frequency, and then we can collect from the other source. Yeah, so some more than one source of the sound. So then the other frequency will be disturbed, yeah, to other, and then we can measure, we can define by the graph of FFT. So that has more than one of source to sound. Yeah. Okay. Then the pattern of the wave. Now we go to the other pattern. We call the to describe the other condition, random waveform. I mean that random waveforms are produced by traffic noise, wind noise, machinery noise, and edge. Noise are randomly processed and never exactly repeat themselves because of different speed, load, and condition. Mean that the condition is different by time. So sometimes we cannot repeat this wave, yeah, to other time. So let's say noise traffic, yeah. So some maybe noise from the Ferrari, some maybe noise from the truck, some noise from the motorcycle. So we cannot repeat this waveform, yeah. So this one is we call random waveform. So we can find from the nature, when wind noise, maybe water, rivers, maybe raining. Yeah. So this one is a very a wave form. Yeah, occur in the capture of the graph. So white noise is a idealist of random noise having same energy at every frequency as could we see in the chart above. Yeah. So some may be good, yeah, because this one is very constant, yeah, sound. So maybe like the raining, yeah, raining, yeah, maybe can repeat, yeah, constant. But this one is still considered also waveform, but the condition is constant, yeah, constant. And then this one is you cannot repeat by tomorrow. Maybe will be different. Uh, this condition we call is white noise. Yeah? Maybe white noise is good for us, like for relaxation. Yeah? Maybe we can hear from the raining frequency. Yeah? We can feel the calm condition. Yeah? And maybe we will be bring us to the stable emotional. Yeah? Is maybe like they use this frequency to treat the uh, what we call for treatment, emotional treatment. The other is a magnitude of sound pressure, other parameter. So you can see, so this one the higher is sound pressure square is a p square, so maybe higher. And then when we call the maybe average, yeah, mean p. And then when we call the peak sound pressure is here, mean is pressure in the higher of peak, yeah. Okay, we can measure this condition, yeah. So I have also project, yeah, to maybe implement in the HVAC system, to reducing, yeah, the noise system in the HVAC, and then we can create one design, and then we can propose the design if we measure and reduce the noise, yeah, in the HVAC system. So we can measure, yeah, by magnitude of the peak, yeah, average sound pressure, root mean square. So we can define by the tool. And then we can capture and represent in the graph. Yeah. So magnitude of the peak itself is the sound pressure of the peak value is only for the few seconds compared to the total length of the sound. This may not give a subjective impression for the sound. So the measurement is a few seconds, the total length of the sound. So another one is average sound pressure for sinusoidal waveform of PR tone for complete cycle. The average sound pressure including reflection and compression is 0. Then we can call this one as average sound pressure. Therefore, average sound pressure is not good either. Yeah. So this one is we try to avoid, yeah, when we design, yeah, in maybe in the area to make the human comfort. So we try to avoid average sound pressure. Yeah, uh, is this one. The average sound pressure is okay, is 0. Root mean square. We go to the root mean square RMS, the best value, so that the positive and negative value one cancel each other. Boson level meter already shown RMS value is related to the intensity of sound and loudness of the sound. So we can measure by loud. We can define by root mean square. So as we know, we can measure root mean square, yeah, by uh, 0.707 from the peak. Yeah. Now we go to the RMS appear tone. Yeah, how to measure. Yeah, just mentioned just now to define 0.707. Yeah, from the peak. The formula is defined by over to square root of 2. Okay, again, crest factor. Crest factor indicate how extreme the peak in the waveform. Crest factor 1 indicate no peak, such as the direct current or a square wave. The crest factor is the ratio of the peak value of the signal to its RMS value. So crest factor can be important for the impulsive noise such as gunfire, explosion, or punch presses for the machine. So we need to avoid this one. How extreme the peak? Sorry, how extreme the peak in the waveform? Crest factor 1 indicate no peak. So we try to avoid the condition of one single of a signal. Mean that when we measure like something, the frequency is starting with the high, yeah, high signal of peak. The only one, yeah, is can also give example like gunfire explosion to mean that one peak only. Boom. So mean that we try to avoid this condition, yeah, to the human comfort. So will be effective to maybe like the high frequency, yeah. Maybe we will influence to the natural frequency of the structure, yeah. So we try to avoid this condition. Sometimes, yeah, high explosion will only, yeah, will be affected to the structure itself by only wave, yeah, wave propagation. So this one is a very dangerous, when to come to the natural frequency number of the structure. So let's say the structure frequency is 200, and then one wavelength, bring to 200, frequency, and then hit to the structure, then the structure will be destroyed. We try to avoid this condition. Okay, we can define by the formula crest, C equal to peak, mean peak in the positive. So how many peak, we try to calculate, and then we try to make this one is in the positive, in that this one absolute information. To mean that no negative, either for the C. So then we try to divide by RMS to pick up the RMS. So we divide. If the indicate no peak is a 1. Yeah. So mean single peak. We don't find the single peak in the graph. If we find more than 1, so mean that one is defined by have the crest in the condition system. Okay, as mentioned before, maybe any frequency will be influenced to the human comfort. So then we can define how to cover this noise from the source. So you can see that from the graph, from the table, they have several source of the noise. Turbo engine is around 170 decibel. So the sun power in watt is if we convert to the sun power is more to 100,000 of the watt. So it is very high to the human comfort. So then after we define this number, what we can do, we try to solve it, maybe by noise absorber, that how engineering works, So and then what else, turbojet, and then compressor, and then what else here, hammer drill, rock band, child screaming, We learn how to describe the decibel condition. Now we go to octave band. Octave, okay, this one I just mentioned before, the octave level of condition. So the first octave, the lower octave, where we try to sing, within the 63 hertz. So if you can sing, more than 7, this one is a very rare, of the singer. So the message from the slide, this bullet informed that in order to make things easier and more organized, we measure sound in band. So we can characterize of the wave, the wave itself. The audible frequency range can be separated into an equal segment called octave band. And then a typical range of the octave band where we measure sound is. So we can categorize the level of the hertz from the octave. And then if we can separate 1/3 octave band, so every level of the octave, we can separate maybe 50, 63, and then 80. We can separate. Level to make classified more easy to us. How dB created? Okay, this one is refer to the first week calculation. Actually, this one is already done in the first week. How we calculate condition. Now we implement to calculate from the example this one from the turbojet 10,000 of the decibel. And then we can calculate to define the sound power by this formula, and then we can use this constant number to convert to the watt, and then because of the number, as we know, the number of the watt is higher compared to the decibel. So let's say we measure the decibel, mean that if we convert to the watt, will be defined by higher number. If we measure in a small number, maybe cannot use decibel, maybe you can use watt. Yeah, so that's how we convert. Yeah, why we use watt, why we use decibel, because watt is for small number. Because compared to the bell scale, yeah, is uh, smaller. So let's say we compare to meter to nanometer, mean that nanometer is smaller compared to the meter. So if you want to measure the small thing, we can use the nanometer, same like the dB and the watt. If you want to measure the small thing, so you can use the watt. If you want to measure the high scale, yeah, high frequency, maybe you can use the unit decibel. Okay, this particle work, yeah, to transform, yeah, of the wave, yeah. So how does a sorry, how does a sound travel? Sound need a material to travel, which air. Sound is a traverse as wave by disturbing air particle. So you need to disturb the particle to make the particle vibrate, yeah, and then hit to each other, and then will transform to other particle. Then we bring to the end of the media. So we higher, maybe we can transform from the air to the solid. Yeah, the air will be vibrate the solid. But if you're weak, the particle of the air just finish, yeah, in the air itself. Now acoustic transmission, yeah, sound can travel through air, liquid, and solid. Yeah, so we have three media here: air, liquid, and solid. Sound travel much faster through the solid compared to the liquid. Yeah, because as we know, the elasticity of the solid is higher. Elasticity. Remember elasticity. Yeah, sound is mechanical wave, which means medium to travel. Now you can see from the figure. Yeah, the figure. This one maybe we can stay the condition of studio. We don't want the disturb condition or when the recording during recording. So what they do, they need a server to avoid the reflection, yeah, from the source. So let's say we need to record only from the singer. So we don't want to disturb by other condition or other source of uh, the sound. So we disturb recording. So maybe the influence to the recording. So what they do, they try to close all the wall by the absorber. Then no reflection will be occur when the recording to reduce strength of the reflected sound of the but many will be sound dull and unnatural. Okay, now diffuser reducing acoustic effect. Yeah, diffuser reduce the strength of the sound bounce by scattering the reflected sound in the different direction so that it will be smooth and interference to the room. So mean that we try to design, yeah, the building by not the flat shape. Yeah? So they will add on the wall or the flat wall by certain shape. Yeah, maybe you can see like the we call pyramid, or maybe some maybe like the curve. Yeah, so this one is a model geometry of the reflection. So mean that the reflection will be go to the other condition, other part, other position. So it's not come back to the source. So maybe we reflect to other, and then they will reflect to other, and then each other will be uh, reflected to other way. So what happen if we try do this? So no more reflected back to the source. So you cannot hear the echo in reverberation in the area to reduce this by geometry shape. Random distribution of sound reflection greatly improve sound quality and consistency for the listener. That's why geometry diffusers are perfect for band and choral rehearsal room and performance space. Auditorium will be benefit with the use of the diffuser on the rear and the side wall. So, so you can hear the condition quality of the sound from the source will be clear. Yeah. So if you use the flat wall, so the reflection will be disturbed. Yeah. The source sound. So that will be make unclear the sound from the source. So we try to make from the geometry. Yeah. The first one, in this video, we develop observer from the observer material. Second is by geometry. Okay, that's different method to reduce. We can combine within the geometry shape to reflected and also the material. So more material, more material, a poor material, and soft, more easy to absorb to the uh, sound wave. And then reducing acoustic effect, combination absorbing and diffusion will give better acoustic. So this one is combination, the combination. So if you want to task, complete, maybe uh, try to test yourself or understand you can complete this task using the software. Play a pure tone on YouTube and see it's a spectrograph. Record random thing around you and observe. Record random noises like white or pink noise. This one is a category like white and or pink noise. Mean that the frequency you can understand. If the even the random but constant. Random and constant. This one we can define as a white. Pink is very randomly, so we cannot define the pattern. Is how you measure your ability, understanding during this class. Okay, I try to make a conclusion. In the this class. So you can explain the basic principle acoustic phase. The basic principle of acoustic phase is from the molecule impacted to each other to bring the vibration, and then you can measure from this phenomena uh, by several parameters like the frequency, period, wavelength, amplitude, and then another maybe like the RMS. You can define by the uh, parameter, and then identify the distribution of the acoustic. How this acoustic can distribute in the uh, area from the medium from the medium. And then the method of reducing acoustic effect from material and also by geometry uh, of the wall design. Okay, that's all for today. Any question?
No,
No,
sir.
doctor.
Okay, for attendance, I try to collect from the system. So let me collect first. To collect Okay, give me some time. Okay. Now I already download the meeting attendant, yeah. So if you have no question here, so I will close the class and then we will see next week, yeah, to continue other topic, yeah. Boleh, eh? So saya close.
Boleh Doktor.
Okay, close. Bye. Assalamualaikum and good morning. So if you have any question, we can discuss, ask in the group, yeah. Okay, that's all. Assalamualaikum and good morning.
Thank you, Doktor.
Thank you, Doktor.
Waalaikumsalam. Thank you Doktor.
Okay, sama.
Terima
Thank you
kasih,
Doktor.
Doktor.
Thank you, Doctor.